So it's a great pleasure to be here today to present with Hans our solution for scaling. Can you hear me? Okay, okay, great. So we'll present our scaling solution for Tezos, and also how we envision that you will be able to build on top of this scaling solution. So this story starts with an observation that it's actually really hard to scale the layer 1 as it is. And if you want to understand that, maybe you can try to picture for a moment the layer 1 as a CPU, a very demanded CPU, that repeats, the fetch and execute cycle to try to process as much operations as possible. And actually, this fetch operations, what it does in something like a blockchain, it actually selects the operations from the mempool and decides which of these operations will go into the block, which is some kind of buffer that defines what will be executed next. This is slow because it requires a consensus, and this consensus is over network, so that's why it's slow. And the execute step is about taking the operation and updating the state of the blockchain to interpret this operation. And it also takes time in the case of Tezos because we really want anyone to participate in the system. And so even a Raspberry Pi should be able to validate a block quite quickly because that's also a real-time system. You have timing constraints. You need to produce a block every 30 seconds. So what can you do? Well, you can sweat a lot in front of a blackboard or type or a keyboard and work on very smart optimizations to reach one key TPS, for instance. That's what we did when we optimized the Michelson interpreter, when we introduced protocol-aware in-memory cache recently, and also when very recently we implemented this pipelining in Tezos. Okay, so you can do that, but actually it's not scaling, okay? Because scaling is not about optimizing your CPU, it's about the ability to add more CPUs, okay? So if you want to think about scaling, you have to set up a more ambitious goal to make sure that you are forced to think differently. And for instance, you can try to think the system to be able to handle 1 million transactions per second. So your very smart optimizations won't work this time. You have to think differently. And the path that we are following to that end is, as you know, optimistic rollups. So if you don't understand yet what optimistic rollup are about, even though Arthur made a great presentation this morning, let me do a small recap and try to re-explain it. The basic idea of optimistic rollup is to separate two concerns. One is to decide which will be the next operations to execute, and this part will be will stay as the responsibility of the layer 1. Okay, so the consensus will decide that, but the execution will be delegated to other CPUs, to layer 2 solutions that we call optimistic rollups. Okay, so it means that on the one hand, the work expected by the layer 1 will be quite lower in some sense, because it doesn't have to execute the operation, which is quite expensive. And on the other hand, it means that we'll be able to add more components, computational components in the system, and these are the rollup nodes that operate, that execute, that make progress on the rollup. How does that work exactly? Well, you originate a rollup, you get an address, And now, when you have an operation, it can target, using this address, a particular rollup. Okay, so the layer 1 will, the Tezos node will still decide what are the operations, but it's to populate what we call the inbox, the sequence of operations for a given rollup, and that's all. Okay, and what the rollup node does, it has its own state that is inside the rollup, okay, and it interprets the operation, executes them, and updates the states. So it means that the layer 1 doesn't know anything about the state of the rollup, okay? It's totally unknown to it. And for this reason, actually, the rollup node has one responsibility, one extra responsibility, is to commit, to publish the hash of the state on the layer 1. Why do you want to do that? Well, it's to make the system safe. Anyone can actually execute his own rollup node for a given rollup, so it can check that this hash is valid or not. And if it is not valid, so if it's valid, by default it is accepted. That's the optimistic aspect of the rollup. But if it is not, there is a refutation process that can be triggered by this person. And in the end, the layer 1 will be able to arbitrate, to decide if the refutation is indeed valid. And finally, the dishonest rollup node will be economically punished. So a large deposit will be lost. Okay? So that's nice, as Arthur said, because the only thing that you need for a rollup to be safe is only one honest rollup node to operate on this rollup. And that's a solution to scale, because if you want more computational power, just add more rollup. Anyone can add a new rollup. Okay? So that's a simple idea, which is nice. And that's the one that we are currently developing. And as you know, as developer, unfortunately, even if an idea is simple in principle, when you enter into the actual implementation of this idea, you realize that there are a lot of details. The devil is in the detail. So let me just give you a brief overview of what the Skoru subsystem of Tezos is. So Skoru is for smart contract compatible optimistic rollup. Okay, and so I will try to present you very quickly the global architecture of this subsystem, so that you understand basically how it works. So you have four big components. Layer 1, okay, the one that you know, with its protocol, in which you will have some information about the rollup stored in the storage. And this information has been designed to be as small as possible, so that the cost in terms of storage of a rollup is small as possible. We did our best. What you also have is the layer 2, so in which you will find a lot of rollup. And you will have a bridge to communicate between the layer 1 and the layer 2, okay? So that you can call a smart contract of the layer 2 from the layer 1, and the other way around. We'll come back on this. And finally, there is this layer, the data availability layer, that will help us to increase the bandwidth of the system. So let me open a bit more the boxes, okay, here, and in particular the rollup node boxes. So here you have a big component which is really important, which is the inbox. As I've said, it defines the sequence of operations that needs to be processed by the rollup. And as you can see, you have the inbox is populated by the contents of the block of the layer 1, indeed, not only, contrary to what I've shown before, I lied a bit. Because if you do that, since the blocks are small, 500 kilobytes, something like that, if you need a lot of operations, you cannot put them all in this small block. So what you need if you really want to scale up is this data availability layer that has been described by Arthur this morning. And basically, the idea is that you want rollup nodes to download only the data that it needs, not all the data of all the rollup nodes. Okay, so we have a notion of slots, which are 1 megabyte long and updated at each block, that allows the inbox to be populated with many more messages that you would have by only taking the inbox, the message from the layer 1 block. Okay? So I won't go into more details, but as Arthur said, what is really important by this, with this layer is this ability to significantly increase the bandwidth of the system without forcing all the nodes to download everything. Okay? So that's something that we are implementing. And if you continue into the box that are inside the box of the rollup node, what you will see is 2 virtual machines. So we have 2 virtual machines in a rollup node. Why? Well, we have a virtual machine which is fast, which is really optimized to execute as fast as possible the L2 operations. Okay, so that's a classic virtual machine that you can find for WASM or I'll talk about that. We'll talk about that later. Hans will talk about that actually later in the talk. But we also have another most exotic notion of virtual machine, the proof-generating virtual machine. So these virtual machines are not for efficiency, but for to act as a source of truth about the semantics of the L2 operations. Okay. You can see it as the rules to execute the L2 operations. And actually, this proof-generating virtual machine is that you will find in the rollup node is a duplicate of the proof-generating virtual machine. I will say PVM now because it's too long. That is defined by the Tezos protocol. So it means that the Tezos protocol gives you the rules to execute the rollup node, and then you can execute it with anything you want, but you have to comply to be compatible with this. Why? Because during a refutation, that will be the component that will produce a proof to show that some commitment is wrong or not. Okay? So if you continue, you will see this outbox. So the outbox is the place where the rollup will put messages from the L2 to the L1. Okay? And actually, this allows to call Michelson smart contracts from the L2, but all these communications, the L1, L2 bridge, is based on asynchronous communication. Why? Because it takes time to process messages, obviously, but also because you need to wait for the state of the rollup node to be finalized to be able to actually execute these messages. Again, why? It's because these messages may contain assets. So you want to make sure that the commitment is really valid, as it cannot be refuted before actually doing the transfer. Okay? Makes sense? Any question for now? Yes?
What does the proof look like?
Hans will show you one. It's a bit abstract for the moment, but we'll go into more concrete examples in a moment. Okay? So that's a global view about the SCORY subsystem. I will just take a little moment to expose what refutations proof looks like in an abstract way, and then Hans will show you a concrete example. So you may wonder what is exactly the difference between Toru, which has been part of Jakarta, and the SCORY that we are currently we have shipped in K, and we are continuing to develop. Well, the key difference is in the shape of this proof. Okay. So in the case of Toru, actually, when you have a commitment in which you agree and another one on which you disagree, as someone that wants the rollup to be valid, Well, what you can do is to look at all the L2 operations that you have here and construct a proof, okay, that will pass in a L1 operation and say, here is a proof that this commitment is wrong. And that's a single operation. So that's nice. It means that you know very quickly that someone has cheated. But the problem with that is that it limits the complexity of the L2 operations. Why? Because Tezos operations are 32 kilobytes. They are limited in size. And so the proof cannot, well, it more or less describes the transition from a state to another one. And if you can imagine that if you have a very complex computation, the transformation can be quite large. Okay? So that's why in the case of Toru, we restrict the semantics to only transactions, because they can be described as very compact, in a very compact way. But still, you have a limit on the number of transactions that you can handle between two commits, because you need to make sure that you can always produce a proof that fits in an L1 operation. So that's a limitation, and Skoru frees us from this limitation, exploiting an idea from Arbitrum, another optimistic rollup that has been developed previously. The basic idea is to move from a single operation, a refutation which is based on a single operation, to a refutation which is based on multiple operations. When you allow yourself to use multiple operations to solve a dispute, then you really unlock arbitrary computations. So I will explain why now. First of all, in our design, to refute is actually, there is not a difference between committing some claim about the state and refuting this claim. Actually, if you want to refute a claim that H2 is a valid hash for the state of the rollup, what you do is to also commit, but with a different hash. Okay? And then it means that there is a fork in the tree. There is not a single line and single branch in the commitment. And so at this point, the system says, oh, since the fork, I cannot finalize, we say cement in the case of rollup, it's the same thing as finalized, after this fork, because there is a conflict here. So if one of these two guys wants the rollup to actually progress, it needs to start what we call a refutation game. So what is a refutation game? So it's a game in which you will try to find who's right. And to do that, you first need to understand that in between the two commits, actually, there have been a lot of computations, okay? And any computations can be represented as an execution trace. So what's an execution trace? It's simple. It's a sequence of state of the virtual machine. And between each state, there is a very simple execution step, like, I don't know, updating a register, popping something from the stack. Okay? So these small steps are really simple. And we call them ticks. Okay? And if you agree on this one, but you disagree on the final state, it means that there exists a first tick in which you disagree. And the first step of the game is to decide what is this first tick. To do that, as Arthur already explained, what you can do is to use an iteration of a dichotomy in which you say for the first player to play, okay, I will provide you 32, I will cut this execution trace in 32 sections, okay? And I will give you for each intermediate state the hash that I have. Okay, so I send it to the other player, and he now has to decide what is the first section on which he agree on the initial state and disagree on the final state, and that's a new refined execution trace. And you have divided by 32 the size of the execution trace. Of course, if you iterate this process, very quickly, you will go in, you will reach a section of a single tick. Okay? And actually, the single tick, as I said before, is a very simple execution step. So the proof is easy, it's small, sorry, and it can fit in a L1 operation. Okay, that makes sense? So the final move of this game is when you reach this single tick refutation step and you provide the proof as with Toru, but using the PVM that your hash is the correct one. Okay? Make sense? Great. So it means that with 4 operations, you already have 1 million tick. And with 10 operations, you have execution trace, which is probably older than the universe. So that should be enough. That means that you can unlock, you can do arbitrary computations here. Okay, so that's the moment when I wrap up the first part of the talk. And if you need to take home some message, maybe the first one is that indeed optimistic rollup allow to scale for 2 reasons. Because data availability layer allows us to provide bandwidth to publish a lot of TPS. And fast nodes will provide computational power to execute lots of TPS. Okay? And if you need more TPS, just add a new rollup. That's all. There is a bonus. In the architecture that I've shown, the PVM is abstract. And that's because using the fantastic module system of OCaml, we were able to actually implement the protocol, the score system, as a functor, so a parameterized module, sorry. So the parameter is the PVM. So it means that if you need more interoperability, you just have to implement a new PVM. So that's nice. So it's time now for Hans to talk.
Thank you, Yann. One thing that can make optimistic rollups a little bit hard to understand is that they blur the line in some sense between core and applications. So there are actually multiple ways for a developer to contribute to a rollup by working on different parts of the stack. You can work very close to the core protocol, or you can work in a very similar manner to how you would work as an application layer developer in a traditional blockchain. So what I'm going to try to do now with this part of the talk is to talk a little bit on how we went about implementing support for the WebAssembly instruction set for the Score architecture, and also give some examples on the different layers of the stack that you can work on as a developer in this system. So if you think of this as a virtual machine, this is a virtual machine that runs some instruction set, and like Yann mentioned before, the Score protocol itself can support basically any kind of instruction set that you can think of. So the first thing that needs to exist is a PVM instruction set, which is just a module in the Tezos protocol. So at the moment, we are developing one of these virtual machines as a module in the Tezos protocol, supporting WebAssembly. And this gives the ability for a person, which we call the rollup operator here, to originate a rollup using this instruction set. So the role of the rollup operator is very simple. They have to say, I want to originate this rollup. I have to pick the instruction set that the rollup is going to use. And finally, I have to give the actual program written in this instruction set that the thing is going to run. So this we refer to as the kernel. And that's really all the rollup operator does. So it's very important to note that this is a one-time operation. After you have originated the rollup, anybody can post messages to it. So we don't lose out on decentralization in any way. And if we end up adding the ability for this machine to upgrade itself, we're going to make that probably via having some kind of governance mechanism inside the rollup itself, just like we do on the layer 1 protocol. So that's a very, very important thing to note. Also, like Yann mentioned, it's possible to launch a layer 2 node that actually performs this computation, performs commitments and refutations, and these nodes can also be launched by anybody. So it's very important to note that whenever we talk of a rollup operator, it's really a matter of originating the rollup once, and then later on, it's really something that anybody can do, starting a machine to run the layer 2 node, to deal with your commitments, produce refutations. So the second type of user we have here is a person who actually wants to develop an application on this stack. So one way you can do that is that you can use an existing rollup and you can originate contracts on that. We're going to see some examples of that in a second. And the third type of user here is an end user that interacts with the system just like you would do with a traditional dApp that has been developed on a layer 1 blockchain. So that's the high-level picture. So I'm going to dig down now in some details about the WASM implementation, and then at the end we're going to go back to talk about exactly how you can work with this system. So like Yann mentioned, we have 2 VMs. We have the proof-generating virtual machine, which acts like the reference interpreter for this system. This is written in a camel, and it is based on the official reference interpreter for WebAssembly. So we have made some modifications to this. The most importantly, we have made it deterministic. Because it's a blockchain, we have to be deterministic. There can't be any ways, we can't in any way depend on, say, the execution environment, the hardware, for example. And the second thing that we have done is that we have tickified this. So we have broken it up into small execution steps. So we're going to see an example in just a second. We're also developing a layer 2 node that includes a fast VM, and this is using an off-the-shelf WebAssembly VM. So our goal at the moment is to run 5 times slower than native. We hope to improve this later on in the process. And why is it 5? Why isn't it 1? Well, this is because we rely on JIT compilation, but we don't want to be able to use just any JIT because that opens us up to several types of attacks. Somebody can send kernels that trigger a particularly slow part of the JIT compiler and forces the whole system to go down. So we need to avoid that. And it has also been instrumented to behave like the PVM. So this is how we make sure that the fast VM and the proof-generating virtual machine are always in sync. So the plan here is that we're going to use the fast VM by default. We're going to take snapshots, say, every 20 seconds. So a snapshot here means that we have a complete image of the entire execution trait of this machine. So that includes all of your memory, the execution state of your program, what function is currently executing, and also all of your durable storage, what you would traditionally think of as your file system or your context. In the case of a refutation, we're going to replay execution from one of these snapshots on the slow PVM. So that's how we're going to generate the refutations. So Yann talked before about state transition proofs. So what is a state transition proof? Well, it is a specialized form of a Merkle proof that shows the state or a projection of the state before and after one tick of execution. So what does that mean? What is one tick? Well, we can think of a tick roughly as a unit in time or equivalently as a unit of gas, because gas is how we tend to measure time in blockchains. Another way we can think of it is that it is one step in the reference interpreter. So not the fast VM. The fast VM, of course, can use different strategies to achieve fast performance. They might use JIT compilation. They might use some very clever type of interpreter that has been optimized to run fast, and so on. So that's why we rely on the reference interpreter to define exactly what one tick means. Okay? And as before, proofs are generated by these nodes, and they're going to be checked by the layer 1. So here is a WebAssembly module. Let me try to read it out in case the text is too small. So WebAssembly by default is a binary format, by the way, but you can also convert it to this S-expression format, which looks a bit like Lisp, but don't let that deceive you. It really is an instruction set format. So what this thing is doing is we're defining a module. A module is the top-level compilation unit in WebAssembly. We're saying that it's going to have some memory. So it's going to have a vector, a big vector of bytes. Finally, we're defining a function, which we're going to call test. We're going to export it. And the function is consisting of these 4 instructions. And again, deceivingly, this looks like a function call and like an expression with nested parameters. But this is just syntactic sugar in this format. In the binary format of WebAssembly, it doesn't even look like this. In the binary format, this means const instruction of 0, which means push 0 to the stack. It's a stack machine. Const instruction of 55, push 8000, and finally call this memory fill instruction. So that means we're going to push these 3 operands, and finally we're going to push memory fill. So the meaning of this instruction is that we want to copy one chunk of memory to another. So it's like mem copy in C, very low-level, simple instruction. And these 3 parameters that are on the stack before you execute, it's going to be a pointer, which is an offset in memory. It's going to be the number that we want to write. Sorry, I said copy. This is actually fill. So what this instruction is doing is that between this offset and for n bytes, this number here, we're going to write this value. So it's memfill. This is the execution tray. So these are the ticks that the machine would actually step through in order to execute this program. So the first one is that we're going to say we're going to invoke test. That's our top-level entry point. And the machine will respond to this by pushing a frame. So whenever you invoke a function in WebAssembly, you're going to get one of these frames on your stack. And the frame contains a reference to a module instance, local variable, and so on, local value stack. After we've done that, we're going to enter the body of the function. And as I said, this is actually the reverse order in the real format. So we're going to push we're going to push a 32-bit integer, 0, 55, 8000. And finally, we're going to run the memory fill instructions. So memory fill looks very much like it's not constant time, doesn't it? It looks like it's going to be linear in the amount of memory it copies. But it so happens that in the interpreter, this is nicely inductively defined so that the semantics of this instruction, memory fill, once executed, is actually to pop these 3 elements off the stack. And, well, let's look at it. So this is how we started, invoke test frame, push, 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 memory fill. So what it's going to do now is it's going to copy just the first byte. Sorry, not copy, fill. It's going to fill just that first byte, write the value 55 after popping these 3 elements of the stack. And then it's going to push 3 new values to the stack. So instead of 0, it's going to be 1. It's still the same value we're writing. 55 is pushed again. And the number is now -1. So 8000 has become 7999. And then it's going to push memory fill again. And then the machine just continue like that until we hit 0, in which case no more instructions are pushed. So this is how something that actually looks like one linear time instruction gets broken down into constant time instructions. So this is just part of how the reference interpreter already works. So this is a Merkle tree that describes our execution state. So this is only slightly simplified, but the idea is that we have some bookkeeping. We keep some tick counter that gives us the current number of ticks we have processed in the machine. And this follows from the structure of the reference interpreter. We're going to have a reference to the top-level module that we're executing in. We're going to have our value stack. In this case, we're going to start with some values at the bottom that we don't really care about, 3a, ff. And the point in the program that I'm showing here is from this slide right here. So just to recap, what did we do? Test, frame, pushing these 3 values, memory fill. That instruction will pop off 3 values of the value stack. That's why we don't see them anymore. And then we had executed this push. So we're going to have 1 on the stack already. And the goal now is to push 55. So the 1 is on the top of the stack. And the final thing that the execution state contains is the continuations, so the set of instructions still to execute. So that's what we see down here. So the next step that we're going to do is 55, and then we have the rest of the trace there. So this is what it looks after. So the paths that have changed are highlighted here in red, of course. So the tick count has increased from 7 to 8. 55 has been pushed on top of the stack, and we have popped 1 instruction from the continuation. That's it. So the whole idea of the system is that we progress in these kind of small steps that all perform a very, very slight rewriting of the tree. So that's how you execute general purpose computation. Of course, WebAssembly, Turing-complete instruction formats. You can compile, your C program, your Rust program. But in order for this to actually be useful, we don't just want execution. We also want to be able to interact with the system in which we're running. So this is where host capabilities come into the picture. So host capabilities provide us with an API that we can use to write kernels. So they are provided by the VM. They're part of the PVM specification. And they provide particularly access to the durable storage so that you can read and write to your Merkle tree. This is how you get your file system. They provide a bridge between the layer 1 and the layer 2, which allows you to communicate between layer 1 and layer 2, as Yann explained before. And in particular, you can also use this mechanism to deposit and withdraw assets in the form of tickets, Tezos tickets. And we will also provide other functionalities, gas metering, which will give you an idea of how long has this machine been executing, what is the current tick count. Because we have that data, why not just give it to the kernel? It might be able to use it. So this is just a super minimal example of a kernel written in Rust. So important to note here is that in addition to your Merkleized state, you also have access, of course, to RAM, because this is WebAssembly after all, so you will have access to linear memory, just like in any C program or Rust program. So here in Rust, we are actually using RAM to represent the top-level state of our kernel. Very simple. It contains of just 3 integer values, and one of them is boxed. So you can do that. You can put stuff on the heap. It's going to work fine. And it's safe, of course, because it's Rust, it's memory safe. There's some default values, and kernel logic here is very simple. It's just going to fetch some stuff, perform an addition, increment some counters, and this is just simple examples of using the host capabilities. This is a Rust macro debug message, but under the hood, it would invoke a host function that is actually a no-op, that has no effect on the execution state, only exists to print debugging. We also see some examples here of using the input host capability to receive messages from layer 1, send messages back to layer 2, and there is a protocol that we call the rollup management protocol, which defines how you represent these assets, these tickets that the machine receives from layer 1 and sends back to layer 2. So this integrates with the inbox and outbox on layer 1 to make sure that the ownership is always preserved. So these are the examples. So just to recap the high-level pictures, our plan is to have WebAssembly finished in 2022. We're still working on it. It's very much active development. We have written a kernel for this already, which is very similar to Tor. It's a purely transactional kernel that includes BLS signature verification and a very, very, very basic account system. We are starting a work stream now to implement or to take an implementation of the E3 virtual machine, compile it to WASM, and run it inside one of these rollups. And there are also plans for a Michelson runtime environment, probably in 2023. And there are, like Artur said this morning, 2 ways you can do this. You can deploy a Michelson smart contract on a rollup, so the contract effectively becomes the kernel, it becomes the entire rollup. Or you can deploy an entire blockchain inside of the rollup, which has the ability to execute Tezos. So in order to do that, we will put the Michelson interpreter either in WebAssembly or using some other kind of instruction format. So to recap, how do you run your application? Well, it depends on how much control you want to have and how deep you want to go in the stack. So the easiest way to onboard yourself to smart contract optimistic rollups is that you join a large rollup that already exists. So we're going to deploy one of these. We're going to deploy our transaction kernel and probably also one kernel with EVM capabilities onto the mainnet. And we encourage others to do the same. So we have a couple of these big ones. And if you join one of these, it will be just like joining a mainnet. And you will be able to write your contracts in a smart contract language, EVM-based contracts, Michelson-based contracts, and you will get integration with BLS signatures and batches and so on. So that's the easiest way. If you want to do something slightly more low level, you can use a kernel framework to roll your own kernel, which is an experience much more similar to how parachains work in other systems. The kernel frameworks that exist, they can use any language, but primarily Rust and Go and other memory-safe languages are going to be used to develop this. And if you really, really want to, you can, of course, also write a completely custom kernel in C or raw WebAssembly, anything that compiles to WebAssembly, and this will give you maximum flexibility. And we're planning to build a layer 2 node with fast execution that supports all of this. So in summary, please join us. This is very much an active development project, and we're very, very keen for bleeding edge, trying things out, giving us feedback on the design, on the implementation. So the development is happening in these two repositories. In the Tezos repository, Tezos, this is where the main code base lives, the Scorer protocol, and also the WebAssembly PVM and our layer 2 node. The kernels that we are working on right now live in TriliTech kernel. And if you just want to have a chat or if you have any questions, please join Scorer Ecosystem on the Tezos Dev Slack, or reach out to me or Yann. And I should also say we're also hiring core development roles. So if you are an application developer and you want to come over to the other side, we should have a chat about that. So that's all. And I think Yann will come up and we'll take some questions. Thank you.
We have time for a couple of questions.
Is the Scorer protocol formally proved like Tezos protocol? Is it safe to use or is it still beta?
So it's not formally proved. We are following, as usual, lightweight formal methods, in the sense that we have quite precise design documents, as well as some parts which are formalized on paper. It's not certified in COC, for instance, but well, in the long run, that's the kind of goal that we want to achieve. So it's safe to use as the rest of the protocol. It is developed with the same methodology.
Thank you very much. I think this is really crazy shit that you're doing. Super nice. My first question is, do you know the TrueBit protocol, which seems to be very similar in some way? Ever heard?
I don't know it.
Okay, anyway. Yeah. My next question is, how can you consider these rollup nodes together? Are they some kind of side chain then?
Yeah, so the main difference between a rollup and a sidechain is that in the rollup, we are actually making a commitment on layer 1 at regular intervals to the state of execution. And there is, in the case of an optimistic rollup, this ability to refute. So the theory behind all of this is that as long as you have at least one single honest validator active and contributing to the main chain, you have exactly the same levels of guarantees as you have with a layer 1 chain. So with a sidechain, you have slightly weaker guarantees.
Okay, thank you. One third question is, have you any some kind of benchmarking with regards to cost? So for example, if you have an optimistic rollup that has, I don't know, 32 transactions, how expensive would be the refutation, or how you call it, compared to executing them just like that on the chain?
The problem is that you just cannot execute them on the layer 1 because you don't have the state of the rollup.
Pardon?
You don't have the state of the rollup. You only have the hash, so you cannot just re-execute. What you could do is to bundle the operations with the state but it's unlikely that it will fit in an operation, so it would be complicated.
Yeah, perhaps one question for the verification. Is it what transactions are executed on the chain and what are executed off the chain? So for example, if I see there's a fake proof or something, and what operations are then executed on the blockchain and which are off-chain?
So by default, everything is executed off-chain. So it's important to understand that the refutation procedure is something that is not expected to be run in the general case. And the economic theory behind the protocol guarantees that the loser will actually pay for everything that happens by forfeiting their deposit. So it's supposed to be a no-loss situation as long as you behave correctly. Of course, you may accidentally post a bad commitment because you have, for example, a bug in your node.
Okay, thank you very much.
We have time for 2 more questions.
Hello, thank you very much for your presentation. And I wanted to know, so scaling a blockchain is still a very new territory. And what was the main idea, or let's say the business idea, that you wanted to implement within the scaling solution? Was it to have more input? Was it maybe to make it easy to onboard new developers? What were your main idea for scaling the Tezos blockchain and compared to other blockchains?
I think there are 2 main points. One has been explained by Arthur previously, which is to prepare for the future. You want to make sure that if some company grows, some system grows a lot, it needs a lot of TPS and will be able to implement that. That's the first reason. And the second reason is indeed interoperability. So the design of the system will allow us to create more bridges, more ways for people from other ecosystems to come to Tezos, and also maybe to have some cross-chain exchanges, I guess.
What about Z key Stark? Because I find it beautiful mathematics. So why don't you use this technology? It's quantum resistant. Do you use?
So ZK, the problem, as far as I understand, of ZK is twofold. The first one is expressivity. Here we can really express anything. So we are not limited. With ZK, you have to think about the size of the circuits, and it's not easy to actually compile everything to circuits. That's the first reason. The second reason is probably the composition, the fact that it's expensive to construct these circuits. So if you want a reactive system, simple ways to originate and to iterate on software, it introduces some latency in the cycle of development. So I guess if it takes you 3 days to get your compiled smart contracts, it's not the same as 2 milliseconds. So that's the kind of problem that I see, but I'm not an expert of ZK things.
Thank you very much for your answer.
All right, and with that, let's give a big round of applause to Hans and Yann.